talking about inverse circular functions, which is a way to go in the reverse order of what we have been doing. Up until now, we've been given an angle, like let's say pi over 4, and we have determined what, let's say, the sine of that angle is. Or maybe we looked at the cosine of pi over 3. What we'll be doing now is going in the reverse order and saying, I have some angle. I'm not going to tell you what it is. Which angle has a sine of 1/2? Or which angle has a cosine of negative square root 3 over 2? The notation that we use is with a little -1, sorry, written up in as an exponent. And then we're going to try to extract what the angle is. We have a little -1 as an exponent. We put the value of the cosine, and we'll give back what the angle is. This is called the inverse sine or the inverse cosine. Another way that you'll sometimes see it written in books is arc sine and arc cosine. What is the arc length associated with that particular value? Talk about functions that have inverses just in general. So we have this idea of the domain and the range, the domain being all of the x values associated with a function, and the range being all of the y values associated with a function. And suppose we have, let's say, a parabola. It looks like this. We determine whether something is a function by looking at its picture. If we can draw a vertical line anywhere on the function, and that vertical line intersects with the graph in only exactly one point, then we say that that passes the vertical line test and it is considered a function. So this passes the vertical line test. So this is a function. And when something is a function, we give it a special designation. We use the notation f of x rather than just y equals. An example of something that would not be a function would be maybe a circle. There is an equation that we can write that would be the equation of this circle. The unit circle is x squared plus y squared is equal to 1. That 1 on the right-hand side is related to the radius of the circle. And but if I were to draw a vertical line here, it's intersecting the function in 2 locations. So this is not a function. It is a relation. It is a graph that we can see, but we would need to remove half of that picture if we wanted it to, in fact, be a function. Now, the second idea that we have on this slide is something that's called one-to-one. So just because something is a function doesn't mean that it has an inverse. It also has to be one-to-one. So going back to this picture of the parabola, I know it's a function because it passes the vertical line test, but then I'll do something different called the horizontal line test. And I see that this intersects the graph in 2 locations. What that means is if I want to think about this backwards, I say this function actually, let's make this simpler. Let's make it one that we know. Let's make it just x squared so that we can think about the values. F of x equals x squared. And let's say that this is the line y equals 4. So I give you the output value of the function, y equals 4. What was the input that I plugged in to end up with 4 as an output? Well, by looking at the graph and just kind of what we know, there's two options, right? One of them is x could have been negative 2, and the other is that x could have been positive 2. So when I go in reverse, I don't have a single value that I know for certain I plugged into the function to get that particular output. And so this function is not one-to-one. A function that is one-to-one might be something that looks like, let's say, a cubic graph, like x cubed. X cubed looks like this. That also kind of looks like the tangent graph that we graphed before. Y equals x cubed, or f of x equals x cubed. It passes the vertical line test. I can draw a vertical line anywhere and get an intersection in one single point. But then it also passes the horizontal line test. I can draw a horizontal line anywhere and get an intersection point in only one place. So this is a function. And it also is one-to-one. When we look at the inverse functions, we're taking the x and the y and we're interchanging them. You can see here in this notation with this little -1, we took the y and the x values and we switched them. That little -1 that's written up in the place of an exponent is not an exponent, it's just part of the notation that we're meaning, and it doesn't mean inverse. So it's not that we're taking the function and flipping it upside down, it's that we're changing x and y. This slide has a summary of what happens when we find the inverse of a function. The domain and the range switch. So anything that was an x value becomes a y value, and vice versa. And because of that, we get these reflections across the line y equals x. The line y equals x is when we have every value being the same. So some of the points on that line are 1, 1, and 2, 2, 3, 3, etc. And that line kind of cuts through the axis system this way diagonally. So we know, just from our experiences, that if we have the function f of x equals x squared, we know that this function is the inverse, right? I know that I can use square root to get back something that I squared. But let's look at what these graphs look like. The graph of square root of x looks like this. And the graph of x squared we know looks like this. But what we've done is we've cut this other part of the square root graph off so that it would be a one-to-one function and would have an inverse. So this part of the graph is not listed, and I can see that the green and the blue are reflections across that orange line. There are reflections across the line y equals x. And for this this is x squared. For this x squared graph, we're going to only select x's that are greater than or equal to 0. We're not going to consider any negative numbers, and that's what cuts off half the graph. And then also, we know that we can't take the square root of a negative number. So these two kind of match up, right? So now here are some other pictures of inverse functions. This first example is just a singular point with with coordinates b, comma a, and then if we reverse the order, we get the reflection across that line y equals x. And the graph on the right, we have something more complicated. Kind of makes sense that we have something cubed versus the cube root of something, and those are inverses. And the point is just to see that these are reflections across that line, y equals x. I talked about this a little bit in the beginning, that when we have the inverse sign, with two different ways we put the notation, and one is either arc sign or sign with the little -1 written up there. And notice that we have to restrict the area in which we're considering the graph. Let's talk about why that is. Hang on, let me go to, here's the a picture of the graph. The normal graph of sine goes on kind of endlessly in the direction of x and y, right? It looks like this. But what we're doing is, this is at 1, this is at -1. Over here we're at pi. Over here we're at -pi. We're taking the x and the y axis and we're switching them. So you can see, looking at this picture here, that the 1 and the -1 are on the x-axis now, and then I've got -pi/2 and pi/2 on the y-axis. If I were to continue this graph the way that it is normally, right? I'm taking the whole graph and I'm drawing it sideways. I get something that doesn't pass the vertical line test. I can't have two values where you can intersect a single line. So what we've done is we've restricted the graph to just this little portion between -pi/2 and pi/2, so that the inverse is in fact a function of its own. And so when you plug into the calculator any of these inverse sine values, you're only going to get answers that are in between -pi/2 or pi and pi/2. So that would be in quadrant 4 or in quadrant 1. Thinking about the unit circle, this is -pi/2. This is pi/2. So we're only going to get answers that are down here. This will be when the sign is negative, or up here, this would be when the sign is positive. Up here are a couple of questions. You can plug these into the calculator. In the calculator, you won't see arc sign, but you'll see this notation. So this is asking us, what angle has a sine of 1/2? Well, that happens when the angle is pi/6. And so that's the answer for this particular first problem here. For the second one, it's asking what angle has a sine of -1? Well, that happens on our normal unit circle, that happens at 3pi/2, but because we're only considering values in between -pi/2 and pi/2, the answer that we're going to have is -pi/2. So again, the sine is equal to -1 down here. If we were looking at that as a positive angle, it would be 3pi/2. But we're only allowed to consider values either from -pi/2 up to +pi/2 for our answers here. So we go with the -pi/2. And then this third example is asking what angle has a sine of -2? We know that the sine and the cosine, they have maximum values of 1 and minimum values of -1. So this is not an option. And if you plug this into a calculator, you'll actually get an error message, because that's not possible. Here are some examples for cosine. Cosine, similarly, we have to restrict the graph, because if I were to continue with the cosine graph, I would violate the vertical line test. And so for cosine, we're only going to consider values between 0 and pi. So for cosine, we're going to get values that are either in the first quadrant, that's when cosine is positive, or in the second quadrant, that's when cosine is negative. Here are a couple of examples. This first example is asking what angle has a cosine of 1, and that happens when the angle is equal to 0. The angle is equal to 0. It's asking us what angle has a cosine of negative pi over 2. And again, we're only considering the first and the second quadrant. We know that there are multiple angles, but we're only going to select the one that's over here, not the one down here in the third quadrant, just the one in the second quadrant. And so that ends up being 3 pi over 4. You can plug this into the calculator and it'll give you back these answers, but I'm just wanting to show you conceptually what's happening. And then of course we have tangent, and the interesting thing about tangent is that normally for tangent we have these asymptotes that are running vertically, right? So tangent, we know, straddles the y-axis like this, and then we've got asymptotes like this at negative pi over 2 and pi over 2. Notice here that when we take the inverse function, we've got now the asymptotes are horizontal, but that sine graph, or that tangent graph is still sandwiched in between. And though this one is going to go on endlessly, so its domain is all real numbers, and the range, it's going to go, the highest value that it approaches is pi over 2, and the lowest value it approaches is negative pi over 2. But it never reaches those values, and that's why we have parentheses around the range, because the graph never equals those values because they're asymptotes. So here's some general information about tangent. This chart, you can find it in your text. It tells you which quadrants of the unit circle the calculator will give you back for the key trig functions. And for this class, we're just going to focus on the first 3. In pre-calculus, we kind of talk about all of these. We extend a little bit more. But the only thing to kind of think about here is that the domains and the ranges are switching, right? Normally, the domain for sine is all real numbers, and the range is -1 to 1. But we've switched that and then restricted the interval for the range so that we end up with something that's a function. So again, we just want to focus on the first 3, and the pictures that we have in those graphs are helpful. So here's an example of something that you might see on a test, because it involves sort of thinking through a problem rather than plugging it into a calculator. If you plug this into a calculator, it's going to give you a decimal answer, and you won't be able to figure out this exact answer here. So the idea is that this right here is some angle. We don't know what it is. It's asking us, what angle has a tangent of 3 over 2? So what we do is we draw a picture, like we have over here on the right. Tangent is the opposite side over the adjacent side. So we put a 3 across from the angle and a 2 next to it. And then we use the Pythagorean theorem to find the hypotenuse. So we said that 2 squared plus 3 squared will give us the hypotenuse. And so that's where we're getting this square root of 13. We don't have to determine what the angle is. We just want to know the relationships within this triangle. And now that we have this picture, we can determine what is the sine of this given picture. The sine is the opposite side, 3, over the hypotenuse. And then we rationalize the denominator to get our final answer here. Here's another example that's similar. This part here is asking, what angle has a cosine of -5/13? Because we have a negative value, our triangle is going to be drawn in the second quadrant. Cosine is the adjacent side over the hypotenuse. So we put the -5 next to the angle, and then we put the hypotenuse as 13. Using the Pythagorean theorem, we can find the other side. So y is going to be the square root of 13 squared minus, sorry, that's a little, 13 squared minus -5 squared. And you'll get that y is equal to 12. So now that we know what the triangle relationship looked like, we don't need to know the exact angle, but we can say what is the tangent of this triangle that we've drawn. And the tangent is the opposite side, 12, over the adjacent side, -5. And so then we have our final answer here.